Welcome, everyone, to Dansplain. This is the place where we dig into the details and bring you the real story. Today, we're diving into something. Well, honestly, it sounds a bit like science fiction at first.
It really does.
Have you ever looked at, a giant dam or maybe one of those super tall skyscrapers and just wondered, are we humans actually, physically changing the planet?
Not just, the climate or the landscape.
Exactly. But something really fundamental, like the way it spins. It sounds completely out there, doesn't it?
It absolutely does. The idea that our collective building and engineering could actually shift the Earth's rotation or even move the poles, it seems fantastical.
But that's what we're exploring today, right?
Precisely. We're going to look at how these huge projects are, maybe subtly, but definitely measurably, rewriting Earth's rotational budget.
Okay, rewriting Earth's rotational budget. I like that. So yeah, our mission today is to unpack the surprising ways that human megaprojects, we're talking dams, cities, even just how we use water day to day, are actually altering Earth's spin and where the poles are.
And we've got some fascinating sources lined up.
We really do. They basically show us the receipts, the proof of our impact, and honestly, the precision we have now, how we can read those receipts. It's genuinely mind-blowing.
It really is a testament to modern science.
Okay, so let's dive in. Let's start with the basic idea. When we say humans are changing Earth's spin, what's the science behind that? Is it really just about moving heavy stuff around?
Fundamentally, yes. That's pretty much it. It all comes down to moving large amounts of mass on, a spinning object, Earth. Yeah. And the key concept here is something called moment of inertia. It sounds technical, but think of a figure skater. You've seen them spin, right?
Sure, yeah. They pull their arms in and spin faster.
Exactly. When they pull their arms in, their mass is closer to their axis of rotation. That decreases their moment of inertia, so they speed up. Arms out, mass spreads out, moment of inertia increases, and they slow down.
Okay, got it.
So on a planetary scale, when we do things like shift huge amounts of water from oceans into reservoirs, or even build really tall, heavy structures, we're doing something similar. We're changing how Earth's mass is distributed relative to its axis.
And that affects how it spins.
It affects how fast it spins, yeah. And also the exact position of the poles that slight wobble the Earth has.
Huh. So if you don't, feel the Earth suddenly spinning faster or slower when a dam gets filled?
Oh, definitely not. The changes are tiny.
The planet is constantly adjusting, and we're actually nudging it. We're part of that adjustment now. Measurably so.
Measurably so. That's the key. And it's often the cumulative effect, lots of different actions adding up over time.
Right. Not just one single project, usually.
Exactly. And it's our engineering prowess combined with incredibly precise measurement techniques that lets us actually see these shifts happening.
So thinking about these cumulative effects and moving really huge masses, water seems like the obvious candidate, right? It's heavy, and we move a lot of it.
Water is definitely the biggest player in the story, at least historically. Take what some of our sources call the Global Dam Club.
The Global Dam Club.
Oh, yeah. Basically, since around 1830, the start of the Industrial Revolution, humans have built something like over 7,000 major dams across the globe.
Wow, 7,000.
And all those dams hold back enormous reservoirs. They've effectively trapped huge volumes of water on land, stopping it from flowing straight to the oceans. And crucially, a lot of that water ends up closer to the equator than it would be in the oceans.
And moving mass towards the equator slows the spin down, like the skater's arms going out.
It affects the moment of inertia, yes. But maybe even more strikingly, this collective shift of water has actually pushed the physical North Pole.
Pushed the pole.
Yeah. By about a full meter since the Industrial Revolution, roughly towards Greenland.
A meter? Wait, the actual North Pole has moved a meter because of dams?
The Earth's axis of rotation has shifted relative to the crust by that much due to that redistribution of water mass. A meter. About the height of your kitchen counter.
That's incredible. That's a physical reorientation of the planet. It's not just climate change. It's changing the actual geometry.
Precisely. And while a meter over, nearly 2 centuries might sound small to some.
Yeah, I was going to ask, why is detecting that shift so important?
Well, it's significant because it takes us beyond just computer models. This is observed, empirical data. For scientists who need to know Earth's exact orientation in space, and that's critical for GPS, for astronomy, even for tracking sea level rise accurately, these shifts aren't theoretical. They're real, and they have to be factored in.
So it proves our calculations and shows we're actually a geophysical force now.
Exactly. It's a direct fingerprint of our global engineering efforts.
Okay, that really puts it in perspective. And you said it's often cumulative, but can we pinpoint, like, individual projects too?
Oh, absolutely. Some projects are just so massive they leave their own distinct signal.
Like the Three Gorges Dam in China. I remember reading about that one. The scale is just immense. One source said filling its reservoir was like pouring, 16 million Olympic swimming pools into one valley.
It's an almost unimaginable volume of water, 40 cubic kilometers roughly. And when that reservoir filled up, mostly around 2012.
What happened?
Well, the planet's moment of inertia increased just slightly, enough to lengthen every single day by about 60 nanoseconds.
60 billionths of a second.
That's right, incredibly tiny, but detectable. And maybe more tangibly, it also nudged the North Pole about 2 centimeters, towards Canada this time.
2 centimeters from one dam.
Yep. And here's maybe the coolest part, technologically speaking. GPS satellites. Their positioning calculations now have to include a permanent correction factor specifically for the mass shift caused by the Three Gorges Dam.
No way. So our navigation systems literally have a note saying, adjust for that giant dam.
Essentially, yes. Correct for Three Gorges drift. Our own tech is observing and adapting to the changes we make.
That is wild. A permanent footnote for a dam. Okay, so dams are deliberate water moving. What about accidental water moving? Or maybe unintended consequences. I'm thinking about environmental disasters, like what happened to the Aral Sea. That was catastrophic ecologically. Did it also mess with the Earth's spin?
It certainly did. The Aral Sea is a really tragic but geophysically significant example.
What happened there again?
Well, during the Soviet era, the two main rivers feeding the Aral Sea, the Amu Darya and Sirdarya, were massively diverted, mostly for irrigating huge cotton fields.
Right, cotton.
And the consequence was the Aral Sea just shrank dramatically, lost about 75% of its volume.
So where did all that water go?
It didn't just disappear. A lot of it evaporated from the fields and the shrinking sea itself. Then, through the normal water cycle, it rained back down, but often on to land masses closer to the equator.
So another mass shift towards the equator.
Exactly, and geophysicists calculated this shift. Turns out, the shrinking of the Aral Sea slowed Earth's rotation 3 times more than the filling of the Three Gorges Dam did.
3 times more.
Yeah. For a long time, up until about 2005 maybe, the Aral Sea disaster was actually the single largest rotational fingerprint humans had left on the planet.
That's staggering. A regional environmental catastrophe having that big of a global physical effect. Okay, so we've got damming rivers, diverting rivers. What about the water we pull out from under the ground? Groundwater pumping.
Yes, that's another huge one. And maybe more insidious because it's happening constantly all over the world.
How much are we talking about?
Well, one study our sources mentioned looked at the period just between 1993 and 2010. In that time alone, humans pumped out something like 2 trillion tons of groundwater.
2 trillion tons. That's hard to even picture.
It's enormous, mostly from key agricultural zones, aquifers under India, California Central Valley, the North China Plain, places like that.
And what happens to that water?
It gets used for irrigation, mostly, sprinkled on crops. Then a large portion of it evaporates, enters the atmosphere, and eventually rains down, mostly into the oceans.
So it's moving mass from land, often in the mid-latitudes, out into the oceans, distributing it more widely.
Exactly, shifting mass outward. And unlike filling a dam, which is sort of a one-time event,
This is happening all the time.
relentlessly, year after year, and this constant pumping and redistribution, it's actually tilting the Earth, shifting the pole by about 4 centimeters per year.
4 centimeters a year. That sounds like, well, more than the Three Gorges effect, right?
It is. The rate of polar drift from groundwater pumping is actually faster than the long-term average effect from building all those dams combined.
Wow. Okay, so let me get this straight. Just pumping water for farms is tilting the planet faster than building thousands of dams did.
In terms of the rate of polar drift during that specific period, yes, it's a really significant ongoing process.
That's kind of mind-boggling. Our thirst for water is literally changing the planet's orientation, centimeter by centimeter, every year.
It's a perfect example of how a widespread, seemingly normal human activity can add up to have a really measurable geophysical impact.
Okay, so far this has all been about stuff we actively do, build dams, pump water. But what about things we might have caused more indirectly? Are there natural processes we sort of kicked into overdrive that also affect the spin?
That's a really important point. Not everything is direct construction. The melting of the great ice sheets is probably the prime example here. Think about Greenland.
Right, the ice melt there is accelerating like crazy because of climate change.
Exactly. It's not a project we built, it's a process we've essentially unleashed through global warming. And the scale is immense. Since just 1992, Greenland has lost something like 4 trillion tons of ice.
4 trillion tons.
Right.
So even more mass than the groundwater pumping we just talked about.
Yes, in terms of sheer mass shifted. And where does that mass go?
From the pole into the oceans.
Right, so it's moving mass away from the axis of rotation, spreading it out. What does the skater do when she puts her arms out?
She slows down. No, wait. If the mass moves away from the axis, the Earth should speed up, right? Like the skater pulling arms in. This is confusing.
It can be counterintuitive. Let's reset. Skater arms in a stas mass closer to axis spins faster. Skater arms out further from axis spins slower. Ice melting at the pole moves mass away from the axis towards the equator oceans, so like the skater extending her arms. It should slow Earth down slightly. My apologies, I misspoke earlier when applying the analogy directly without clarifying the distribution. The key is where the mass moves from and to. Moving mass from poles to equator increases the moment of inertia.
Okay. So melting ice slows the Earth down.
Actually, the primary effect often cited for Greenland melt relates to the pole position shift, similar to dams but in reverse direction. Regarding spin speed, it gets complicated because of Earth's shape and crust rebounding. But let's focus on the documented effect. The sources indicate Greenland melt has contributed to a shortening of the day, meaning a slight speed up, by about 0.3 milliseconds per century. This counteracts the general slowing trend.
Okay, so Greenland melt is making the day shorter, speeding us up slightly.
According to the specific data cited, yes. It seems counterintuitive based on the simple skater analogy, but the complex Earth system dynamics, including changes in the planet's oblateness and mantle response, lead to this result. It's speeding us up just a tiny bit.
And get this, one of the sources said this effect, the Greenland melt speeding us up, is the only human influence big enough to actually push back against the moon.
Right. The moon's gravity causes tides, and that tidal friction is constantly, gradually slowing Earth's rotation down over millions of years, making days longer.
So the moon is hitting the brakes.
And the meltwater from Greenland, by redistributing mass in just the right way, is slightly counteracting that braking effect. It's like we're inadvertently easing off the moon's brake pedal just a tiny bit.
That is absolutely wild. We've accidentally created a counterforce to the moon. Okay, so water.
Ice.
Massive movers. Well, what about just building stuff, like cities, all those skyscrapers? Does piling up steel and concrete radically make a difference?
It's a really interesting question, and it's a newer area that scientists are starting to quantify. Think about it. Every single ton of steel, concrete, glass that goes into a skyscraper, say, raised 300 meters off the ground.
Yeah.
That's a ton of mass moved slightly further away from the Earth's center of gravity.
So it's like the skater analogy again, but moving mass up instead of just horizontally.
Kind of, yes. It's changing the distribution. Now, the total effect from all the skyscrapers globally, every Burj Khalifa, every Shanghai Tower, is still pretty small. Less than 1% of the signal we see from all the water trapped by dams.
Okay, so not huge yet.
Not huge yet, but what's significant is what it represents. It's really the first time we can point to altering Earth's rotation measurably, not with water, but with buildings, with vertical construction.
A whole new kind of human signature on the planet's spin.
Exactly. It hints that as we continue to build denser, taller cities, this effect, while small now, could become another factor we need to track.
And it's not like we've stopped these massive engineering projects either. Are there big ones happening now or planned that will add to all this?
Oh, definitely. Our sources highlighted China's South-North Water Transfer Project. It's still under construction.
What does that involve?
It's this enormous network of canals and pipelines stretching about 4,500 kilometers. The goal is to move about 45 billion cubic meters of water annually from rivers in the south of China up to the drier north.
Another huge water shift.
A very significant one. Early calculations suggest this project alone could add another 0.02 microseconds to the length of the day and shift the pole by maybe another centimeter.
Tiny numbers again, but
but real enough that NASA's big radio telescopes, the ones they use for very long baseline interferometry to measure Earth's orientation by looking at distant quasars, they'll need to account for it. They're constantly recalibrating based on these tiny shifts.
So even these small nudges require adjustments in our most precise scientific instruments.
That's right. It shows the real-world consequences, even if they're subtle.
Okay, so we've covered dams, the Aral Sea, groundwater, melting ice, skyscrapers, future projects. It's a lot. Bringing it all together, what's the bottom line? Are we talking about anything that actually impacts our daily lives? Should I be worried my alarm clock is going to be wrong tomorrow?
Hey, no, definitely not. Rest assured, your alarm clock is safe.
Okay, good.
Our sources are really clear on this. If you add up all these human effects, dams, groundwater, melt, buildings, the total change to the length of the day is still less than a millisecond, less than 0.001 seconds.
So basically undetectable without super-sensitive instruments.
Exactly. It's completely lost in the noise of much larger natural variations. Things like big earthquakes can change the length of day instantly by microseconds, ocean currents sloshing around, even turbulence deep inside Earth's liquid core. These natural processes have a much bigger effect on the day-to-day rotation than anything we've done yet.
Okay. So the human impact is real, it's measurable, but it's still small compared to Mother Nature's own adjustments.
That's a good way to put it.
But the core physics isn't debatable, right? Every time we move enough mass, especially relative to the axis, we are physically rewriting that rotational budget, as you said.
Precisely. The laws of mechanics don't care if it's a natural process or a human one. Move the mass, change the spin. That's not the surprise.
So what is the surprise?
The real surprise, the truly astonishing part, is that we can now read the receipt. We have the scientific instruments and the understanding to actually detect and quantify these incredibly tiny changes.
We can see our own signature.
Yes. In microseconds added to the day, in centimeters of polar wander, even in those little correction codes needed for GPS. It's an incredible testament to human ingenuity, really, and the power of modern geodesy and geophysics that we can perceive our own subtle planetary scale influence.
It really makes you think differently about our place here, doesn't it? That building cities, growing food, managing water, these things don't just happen on the Earth. They leave a physical mark in the Earth's fundamental mechanics.
It changes the perspective from being just passengers to being active participants, maybe even unintentional engineers of the planet's dynamics.
And it makes you wonder, what other receipts are we leaving behind?
Sure.
What other subtle signatures of our presence are accumulating that maybe we haven't even figured out how to read yet?
That's the provocative question, isn't it?
It really is. Well, this has been absolutely fascinating. Thank you so much for walking us through that.
My pleasure. It's mind-bending stuff.
It really is. And thank you all for joining us on this deep dive into how humanity is, quite literally, moving the Earth. If you enjoyed this exploration, please do like, subscribe, maybe share it with a friend.
And definitely check out the website.
Oh, yes. Visit www.dansplain.xyz, that's XYZ, for more articles, deep dives like this one, products, all the good stuff.
We love digging into these hidden corners of science and history with you.
We absolutely do. Keep curious, keep searching, and keep dansplaining. Until next time, folks.